Okay, so these are our notes for 4.3. We're going to be talking about multiplication rules and what's called a conditional probability. Two events, A and B, are considered independent if the fact that A occurs does not affect the probability of B occurring. We have independent and dependent probabilities. So if they are independent, then all we have to do, the probability of A and B happening is the probability of A times the probability of B. However, if one depends on the other, then the probability of getting A and B is the probability of A times the probability of B, and this bar here means given that A has already occurred. So kind of a useful maybe note to take here, would be to say that this means B given A is certain. So if A is going to occur, right? So we have the probability of A, that took care of A. Now we're timesing it by what the probability of B is given that A has already occurred. We'll look at some examples of these as we go down. Some independent events, tossing a coin and rolling a die, drawing a card from a deck, putting the card back, and drawing a second card. By putting the card back, what happens is we now have all 52 cards to draw from. We could theoretically redraw that card, depending on how they're shuffled and organized. Selecting a marble from a jar and tossing a coin. Two things that are disconnected. So find the probability of these events. A coin is flipped and a die is rolled. Find the probability of getting a head on the coin and a 4 on the die. So probability of a heads and a 4, okay, would be the probability of a heads times the probability of a 4, given that they're independent events. And so that would be 1/2 times 4 out of 6 would be a 4 on a die of 6 would be one option out of 6, or 1/12 would be my probability of getting a heads and a 4. If I'm going to draw from a deck and then replace it, then a second card is drawn. Find the probability of getting a queen and then an ace. Well, the probability of a queen and ace would be the probability of a queen times the probability of an ace. The probability of getting a queen would be 4 out of 52 times the probability of getting an ace. If the cards were all put back, there would be 4 aces and there would still be 52 cards. Those each reduce to 1/13, so that's 1 out of 169 for our probability. When a sample is selected from a large population and the subjects are not replaced, the probability of the event occurring changes so slightly that for the most part, it's considered to remain the same. So here's an example. Harris Poll, which is a poll, it's a company that does polls, found that 46% of Americans say they suffer great stress at least once a week. If 3 people are selected at random, find the probability that all 3 will say they suffer great stress at least once a week. So the idea here is that if I take one person out of 300 million people, the 46% is not going to actually change. If I take one card out of a deck of 52, the probabilities do change. And so it's important to understand, we're talking about a massive pile of people. And so the probability of 3 stressed out people, okay, is the probability of one person being stressed times the probability of the next person times the probability of the next person, which will be 0.46 for the first person times 0.46 for the second person times 0.46 for the third person. That is to say that the probability 46% doesn't change as we remove one person. As we remove one person from the group. So if we calculate that, we get the chance that we find 3 people who are all stressed, great stress in once a week, is going to come out to be 0.097. Okay? Finding someone who's stressed is not hard. Finding 2 people who are stressed and one person who is stressed or is not stressed, that's reasonable. But finding all 3 of them, we start getting down to some pretty small percentages. When the outcome of the first event affects the outcome of the second event, we say that these events are dependent. drawing a card from a deck, not putting it back, and drawing a second card. That means there's only 51 cards on the second draw. Selecting a ball from an urn or a pot, not putting it back, and drawing a second ball. Being a lifeguard and getting a suntan. Does being a lifeguard increase or decrease the likelihood that you're going to get a suntan? Does having high grades impact whether or not you're going to get a scholarship? Those things affect each other, okay? So when the events are dependent, you'll use the second multiplication rule. The probability of A given A and B is the probability of A times the probability of B given that A has already occurred. So let's look at some examples. These will really help you out. 3 cards are drawn from a deck and not replaced. What is the probability of getting 3 jacks? So if I were to do 3 jacks, the first jack would be 4 out of 52. But the second jack, if I drew a jack, right, the next pile, there would only be 3 jacks left in a deck of 51. And in the final draw, there would only be 2 jacks left out of 50. And so these reduce my probability each time in order to make that success of getting 3 jacks. So 4 out of 52 times 3 out of 51 times 2 out of 50 is a really small number. Now, in physics, we would just say, oh, this is really tiny. We're actually going to go ahead and evaluate what this 1 over that e negative 4 is. So this would be 1.81. E negative 4 was the number, which means we move this decimal over 2, 3, 4 times to make 0.123181. That's a very small probability. Drawing 3 cards and getting all 3 jacks is very rare. Okay, getting an ace, a king, and a queen in order. Now, probabilities don't actually have, per se, this order. Whether we get them in order or not, it doesn't really affect that. We just have to get one then the other. The key is to make sure that we're doing each probability independent. So that'd be 4 out of 52 times probability of king. There are 4 kings, but now there are only 51 cards. There are 4 queens, but now there are only 50 cards. And so this probability, because they're different cards, instead of being jack each time, it does make it a little bit easier to get all of these. We've got 4 out of 52 times 4 out of 51 times 4 out of 50. If we calculate that, still a small number, 4.83 e negative 4, which would be 0.000483. Still a very, very small number. I don't know, will the calculator let me turn that back into a fraction for those of you who want to know what that means? No, it won't. I'd have to go through and hand reduce these. Like if I took the 4 out of 52 and made it 1 out of 13 times 4 out of 51 is still going to be 4 out of 51. Can't do anything about that. Times 4 out of 50 would be 2 out of 25. Still going to give me the same number, but now I could think 13 times 51 times 25. 13 times 51 times 25 is 16,575. Whoops. 16,575. And this was reduced to 2, and this was reduced to 1. So that'd be 8 out of 16,575. Okay, let's keep going. At a University of Pennsylvania, there were 5 burglaries reported in 2013, 16 in 2004, and 32 in 2005. If a researcher wishes to select 2 random burglaries to further investigate, find the probability that both will have occurred in 2004. Okay, so the probability that the first one occurs in 2004, there are 16 possible robberies out of 5 plus 16 plus 32, that's 48, 53. That's out of 53. I'm going to times that by the probability that I draw another one, but now there's only 15 robberies to consider out of the 52 remaining. So again, calculating 16 out of 53 times 15 out of 52 is going to give me and we get 0.0871. 0.0871. So much higher probability than those decks of cards questions. All right, but the idea is that we're doing that probability given that 1 has already occurred. Now, let's say that you need to calculate the probability of B given that A has occurred, but you don't have it listed. It's not like a deck of cards where it's a little bit easier to calculate. If you need to figure out the probability of B given that A has occurred, you can do the probability that both occur divided by the probability that A would occur. Okay, so this formula is going to allow us to make some calculations. I'm going to try to come back and go back and forth with this. We'll do a couple examples, and yeah, okay. We're moving along. All right, the probability that Sam parks in a no parking zone and gets a parking ticket is 0.6. Now this is really important. That was the and. Okay. The probability that Sam cannot find a legal parking space and has to park in the no parking zone is 20. This would be the probability of A occurring. Okay. On Tuesday, Sam arrives at school and has a no parking zone. Find the probability that he will get a parking ticket. So N, there's no parking zone. T, getting a ticket. So we're trying to figure out the probability that he gets a ticket given that there are no parking, or that he has to park in a no parking zone. Okay? So we want to know if he's going to get a ticket, given that he's parking illegally. Okay? So if you think about where T and N are in that formula, T is the B, and N would be the A. So this divided by is the division of the probability of N. So the probability that A and B occur, that he parks in no parking and gets a ticket, is 0.06. Now the thing we divide by is the probability that N is going to occur, that he's going to park in a no parking zone. That would be 0.2. If we take 0.06 divided by 0.2, we get 0.3. So there is a 30% chance that he's going to get a ticket given that he's parked illegally. All right? That doesn't sound too bad, but it's only a 6% ticket, okay, that he's going to do both, park illegally and get a ticket. So this actually inflates that quite a bit, given that he's already guaranteed he's parked in an illegal spot. A recent survey of 100 people asked, so okay, yada, yada, yada. Find the probability that a respondent answered yes, given that the respondent was female. So what this tells me is we're doing probability of yes, given that F has occurred. That's the probability of Y and F divided by the probability of F. Now we could do this just by kind of analyzing which group to focus on, but the probability of yes and female is 8 out of 100. So that's 0.08, 8 out of 100, divided by the probability of being female, which is 0.5, because it's 50% of the population. Well, 0.8 divided by 0.5, just make sure we're right, 0.08 rather, divided by 0.5, it's going to give me 0.16. That means that 16% of the people, or 16% of our female female soldiers are going to say yes to that answer. Now, what's the number in terms of male? Male seems a little bit higher, okay? Whereas women seemed like in this survey they were saying no. They weren't as highly likely to say yes. The last thing we're going to talk about is the probabilities for the phrase at least, okay? Use 1 minus the complement to find the probability of the given problem. Okay, if I say a coin is tossed 4 times, what is the probability of getting at least 1 tail? Getting at least 1 tail can be tricky because I have to consider the probability of getting 1 tail, 2 tails, 3 tails, or 4 tails. It might be simpler to find the probability of not having at least 1 tail, which would mean 4 heads. Okay. Now the probability of getting 4 heads, that's easy to calculate. That's the probability of 1 heads, which is 1/2, times another heads, times another heads, times another heads. So this is the probability, it's 1/16. That is the probability of getting 4 heads when I flip a coin 4 times. But that's not what I'm being asked. I'm being asked, what's the probability of getting at least 1 tail? Well, if this is the probability that has no tails, then getting at least 1 tail would be the complement or the opposite of this. So the probability of at least 1 tail is equal to 1 minus 1/16, or 15/16. And so that's how we can use the complement to help us with things like doing an at least problem. All right, guys, good luck, and we'll see you in class.